Right. Okay, now continuing with wireless LAN operations. We first look at wireless topology modes. We have the ad hoc mode, the infrastructure mode, and tethering. The ad hoc is used to connect clients in a peer-to-peer manner without the access point. So basically what the ad hoc is an is a topology mode which allows clients to directly connect to each other. Two clients, communication between those two clients. Examples, we have Bluetooth, Wi-Fi direct. So if I have Bluetooth on this device, I can communicate directly with this device. Bluetooth, Wi-Fi direct. I no longer see our smart devices having smart Wi-Fi direct, but I used to have a phone with Wi-Fi direct, very fast, right? So that is an ad hoc mode, direct communication between two clients. Both clients can either be the transmitter or the receiver. That is ad hoc. No access point. We have the infrastructure mode. We now have an access point here, used to connect clients to the network using an access point. So that is the infrastructure mode. We have tethering, which is a variation of ad hoc. When a smartphone with cellular data access is enabled to create a personal hotspot. This is what we do with our phones. You create a hotspot, you share your Wi-Fi, and clients get access to the internet. This is what we call the hotspot, tethering, right? So three topology modes. In this module and in the configurations module, we will basically focus on the infrastructure mode where we have connection via the access point. BSS and ESS. So we're going to define a couple of terms here. The infrastructure mode defines two topology blocks, the basic service set and the extended service set. The BSS uses a single AP to interconnect all associated clients. Clients in different BSSs cannot communicate. So this is a BSS. This is another BSS. So two separate service sets, they cannot communicate with each other. It's two separate BSS. Two separate areas. This is the basic set area. Two separate IDs. Basic SSID, separate IDs. With the ESS, this is basically where if these two can communicate, they communicate via a wired network. This is our wired network. It is now called an ESS. So two blocks that we define the BSS, where we have one AP sharing its network with each client. The ESS, multiple APs are interconnected. A union of two or more BSS is interconnected by a wired distribution system. Clients in each BSS can communicate through the ESS. Right. The frame structure. 802.11 frame format is similar to Ethernet frame format, except that it contains more field. With the Ethernet frame, I think we did the Ethernet frame. We had our source MAC addresses, destination MAC addresses. I know we had the FCS, the frame delimiter, etc., etc. That was the format that we used with Ethernet frame. This one is a bit different. Right? It has the frame control, which specifies the frame type. The frame control specifies the frame type. If we have management traffic, that it is a different frame type. Management traffic, control traffic, data traffic. They have different type of frames. So the frame control, this one here, it specifies which type of frame that we are using. We have the duration. Okay, I know of the addresses. These addresses are your source and destination addresses. We have the duration field. This one is used to coordinate access to the wireless medium. So we'll see and we'll describe the duplex transmission, half duplex transmission in wireless networks. It's not full duplex, it's half duplex. How do wireless devices communicate? How do they know when to communicate? So the duration helps in that coordination. If there is something on the medium, then a client does not communicate until there is nothing on the medium. We'll get there. But this duration field, it serves just to coordinate access to the wireless medium. Right? We have what else? We have also the address, the sequence control. What's that? The sequence control, it has the sequencing number and fragment information, just used for sequencing. Then lastly, the FCS, we know of this one, layer 2 error detection, error control. FCS is used for layer 2 error control. All right, so this is basically the 802.11 frame, the wireless LAN frame. It's a bit different from the, almost the same though, almost the same. Huge difference is we have multiple addresses here, address 1, 2, 3, 4. Probably not the right time to get into those addresses. What's the difference? But those are the source addresses and the destination addresses. All right. CSMA collision avoidance. Wireless lines are half duplex and a client cannot hear while it is sending, making it impossible to detect a collision. Half duplex. Why is wireless communication half duplex? The reason is because we have what we call a shared medium. The air that we use is a shared medium in wireless communication. In wired communication, the reason why we can have full duplex is because you can have a wired channel which is dedicated for specific traffic, therefore very easy to have full duplex. But here in wireless communication, we don't have that. The medium is always shared. So therefore, we have what we call half duplex. And wireless LANs uses carrier sense, multiple access with collision avoidance to determine how and when to send data. A wireless client does the following. So with wired networks, I think we had CSMA, this is collision avoidance. With wired networks, we had CD, collision detection. So before we had our switches, which helped with removing the half duplex, having the full duplex. Before we had that, we had this algorithm, CD, collision detection, which helped. If you want to send traffic, you first send, what do we call it? You first send a signal to see if there is something in the channel. Then you then send your message. That is collision detection. With collision avoidance, almost the same thing. There is a message which is sent, the RTS, ready to send. Ready to send message sent to the AP to request dedicated access to the network. If you get a response, the response will be clear to send. Clear to send, therefore you are granted access, a client is granted access to send. If you don't get that message, it means there is another client which is sending over the shared medium. Then we have to start the whole process again from listening, sending an RTS, receiving an CTS, then transmitting your data. So key points here, the Wi-Fi, it is half duplex. You cannot send and receive information at the same time. Half duplex. Right. Wireless client and AP association. For wireless devices to communicate over a network, they must first associate with an AP or a wireless router. Wireless devices complete the following 3 stages. Discover a wireless AP, authenticate, then associate. So basically what we have here is how you discover an access point. Take an access point as if it's your smartphone sharing your hotspot basically. So kana uri kushare hotspot yako, one, you have what we call the SSID. Is it explained, Pambera? Okay, it's the SSID, which is the name of the network. It is broadcasted. You can share your hotspot. If you enable your hotspot, then everyone within coverage area of that network receives. Open a Wi-Fi yake, anaona kuti my Wi-Fi names and aripo Wi-Fi which I can connect to. I have these names ABC. That is discovering a wireless AP. So you discover the SSID. If you cannot discover it, probably it is hidden. Unaita type the name directly. Try that with your smartphone. It's the same thing with the access point, right? So after discovering a wireless AP, there is authentication. Wakliga Wi-Fi name yako password. You need authentication. Basically, authentication is verifying identity of a certain device and then granting access. Kana usina key, kana usina the password, you will not be able to access the network. Even if you not network iripo, you won't be able to access the network. Right? That is authentication. Then after authentication is done, a device is granted access, and that is association with the AP. You can now send and receive information over the wireless network. So that is the process from discovering an AP to association. To achieve successful association, a client and an AP must agree on the specific parameters. The SSID, which is basically the name of the network. The client needs to know the name of the network to connect, the password required for authentication, the network mode. What is the network mode being used? I talked of compatibility when I introduced the standards. So if the standards which are on the AP are different from the standards which are on the client, in terms of compatibility, you won't be able to access the network. So that's one another parameter which must agree which must be agreeable between the AP and the client. The security modes, the security parameter settings, we have WEP and WPA. Right, WEP, wide equivalent privacy. So these are two types of let me say protocols, security protocols that are used. The WEP, if you go to your smartphone, you see the protocol that you use for encryption and authentication is WPA2. Go to your smartphone, you see that WPA2. Right, channel settings, the frequency bands in use. So these are the parameters that the clients and the AP must agree on. If they don't agree, therefore the clients will not get access to the network, basically. Right, passive and active discover mode. Wireless clients connect to the AP using passive or active scanning or probing. Passive, an AP openly advertises its services by periodically sending broadcast beacons containing the SSID, supported standards, etc., and security settings. The active mode, wireless clients must know the name of the SSID. The wireless clients initiate the process by broadcasting a probe request frame on multiple channels. A lot of English there. Passive mode, the AP broadcasts its SSID. I gave analog of your smartphone. The moment paunesa Wi-Fi hotspot on, if we have passive mode, then your SSID is broadcasted to every client within your coverage area. So munarango is a Wi-Fi, then I have your Wi-Fi name. What your device is doing, do it with passive mode, where there is the SSID being broadcasted. If you're not broadcasting the SSID, then we have the active mode, right? You need to know the name, the SSID basically. You need to know the name of the network to connect to the network. So if a client doesn't know the name, they won't be able to connect to the network. If the client put it this way. By active mode up, unogona kutofamba nemunhu akari kushare hotspot yake, but you won't even see the name because it's not being broadcasted. So those are the two types of scanning that we have, scanning processes, the passive mode and the active mode. You can use, probably you don't have access points, you can use your phone. Shared tethering, there is a mode tethering that is sharing your Wi-Fi hotspot. You can use that. It has the same things that I'm explaining here. CAPWAP operation. CAPWAP control and provisioning of wireless access points. CAPWAP is an IEEE protocol that enables your controller to manage multiple access points. It is based on the lightweight access point protocol, but adds additional security, DLTS, datagram transport layer security. It encapsulates and forwards wireless clients traffic between AP and WLC, the controller over tunnels, UDP ports. Take note of this. These ports 5246, 5247, operates over both version 4, version 6 using the protocol 17 for version 4 and 136 for version 6. So what is CAPWAP? It's just a protocol. It's a tunnel with security. If your access points wants to communicate with your controller, it uses that tunnel, CAPWAP. So it's just a tunnel which is used for communication between the access point and the controller in basic terms, right? Any communication that is between the AP and the WLC, it is via that protocol there. Right, I highlighted my ports are, I think it's very important. At times you have your LC, your controller and your access point not communicating with each other. Because my ports are ngakavharwa pa-firewall. If those ports are not open per firewall, then your controller will not be able to communicate with your access point. We'll probably get there by Chatama configurations. So for there to be communication, those ports need to be opened if you do have a firewall. Right, split MAC architecture. The CAPWAP split MAC concept does all the functions normally performed by individual APs and distribute them between two functional components. Right, with the AP and the controller. Number two, the controller mainly does authentication, right? With a standalone AP the AAP, the autonomous access point, runoita zvese, ndo rinosenda ma-SSID, scanning ndakati kutaura, ndo rinoita authentication, it does everything on its own. But kana tane lightweight, tane the AP and the controller. Now, AP runoita which functions, wireless LAN controller runoita which functions. So we have what we call the CAPWAP split MAC concept, which separates my functions at the access point near the controller. The AP has the following functions right here: beacons, probe responses, packet acknowledgements, frame queuing, MAC layer, data encryption, decryption. And you can see the controller does authentication, association, reassociation, frame translation, termination of 802.11 traffic on a wired interface. In simple terms, the AP is responsible for wireless client connection. It's the one responsible for data transmission because it's the one connected. Nobody tangle data transmission is the one connected to the client. It's also responsible for real-time operations like beacon generations. Ndo panoiswa broadcasting SSID, the passive modes, the active modes. Irikuitika pa-access point. So that is the function of the access point. And your controller is responsible for providing centralized management. Centralized management, managing other APs. It's not responsible for the broadcasting, YEMA beacons and broadcasting, YEMA SSID and all that. Centralized management of all access points in the network. Authentication. Later on, we'll see authentication at times. It will be passed on to my servers. But in this case, the WLC, which is the controller, is also responsible for authentication. Those are the main functions. So centralized management, authentication, and policy enforcement. If you want to change, if policy changes, if you want to change how the APs behave, that is policy enforcement. It is done from the controller. Right. Let's go. DTLS encryption, datagram, transport layer, security. It provides security between the AP and the WLC. So to introduce a KPWAP, it's just a protocol which opens sort of a tunnel for communication between your access point. Okay, I have something there. Your access point and your controller. Okay, I have a question. Since controller in a translation year, so does that mean standards 802.11, yeah, 99 can communicate near 2021? Since in a translation, compatibility, if controller redu richikwanisa kusupporta standard ya 1999, which is highly unlikely, then it will be able to communicate. It just depends with controller raushandisa, does it support that standard? I won't be able to know now specific standards which operate with specific controllers. I'm not privy to that information. Kuti controller rakati rinosupporta mastandards api. But if it does not support standard rinoshandiswa neclient or rinoshandiswa neAP, then there will be compatibility issues. There will be no communication. So I'm responding to question yaskwa kuchat. Right, continuing. GTLS encryption. Right, so now I was saying we've introduced KPWAP. KPWAP is just a tunnel. Take it as a tunnel. Okay, take it as a tunnel, which is used for communication between the access point and the controller. VPN is just a tunnel. You create a tunnel over the public internet so that you can communicate securely. That's the VPN. You can communicate securely between devices. VPN is a tunnel created. So KPWAP is also a tunnel created over your network so that there is communication between your AP and your controller. Where does KPWAP get its security? Its security comes from DTLS. So DTLS offers security of traffic transmitted over the KPWAP tunnel. It is enabled by default to secure the KPWAP control channel and encrypt all management and control traffic. Right. All management and control traffic is encrypted by default. So every traffic which is being used for managing my APs, controller don't manage an AP, it sends management traffic. Could you change your SSID to this? Change your DHCP scope to this, use this set of addresses. That is management and control traffic being sent. It is by default enabled to encrypt that sort of traffic, which is different from data encryption. So if you want to send information from a client to the AP, to the controller, then to your distribution system, that information is not enabled by default. You need licenses. So probably this is just a way to take my licenses on your controllers. If it is not licensed, you can have your controller, but information you are transmitting, it is not encrypted. It is not secure. So I had to highlight those two differences. Your management traffic It is encrypted by default, but your data traffic, you need licenses. Marketing. Flex Connect APs. Flex Connect enables the configuration and control of APs over a one link, wide area network link. There are two modes, the connected mode, the standalone mode. With the connected, the controller is reachable. With the standalone, the controller is not reachable. The Flex Connect access point has kept-up connectivity with the controller through the tunnel. The controller performs all its functions via kept-up. With standalone, the Flex Connect AP has lost connectivity and the access point assumes some of the WLC functions, such as switching client data, traffic locally, and performing authentication locally. All right, let's look at the diagram. How best can we go through Flex Connect? Let's look at the diagram. In the diagram, we have two offices, the branch office and the corporate office, separated by a very large geographical area. So this is a one, let's say this is a one. Here, we have a one connection here, wide area network, right? Tida kuisa ma-access points here, ku branch office here. Does it mean if you want to manage that access point yataisa ku branch here, probably a bit far from our corporate office, does that mean we need to have a controller in that office as well? We have corporate office and branch office separated by a large geographical area. Does it mean it has an access point? Ku branch office red, we also need to put a controller there. The answer is no. And the answer is Flex Connect. So if you want to control your access point over a one link, function is Flex Connect, basically. So you can control your access point yako over the internet. Basically, by definition, that is what Flex Connect is. Now, the two modes, number one, the connected mode, your controller is reachable over the one link. So there is communication between the controller and the AP, these two. There is communication between these two. Is reachable, is called the connected mode. When the controller becomes unreachable, we have what we call the standalone mode. This is no longer here. Therefore, the AP will behave as a standalone access point. Probably it behaves as an AAP at this time. So Flex Connect is configured so that we can have access of my access points edu are probably a bit far away, but here, so we can be able to connect to those access points over the internet, which is our one link in this case. Let's just say the internet to simplify things. Flex Connect, connecting to the access points over the internet. Channel management. Right, maybe back here, you probably understand Flex Connect much better, but share my configurations. There is actually configuration. It is very important. Yet here, Flex Connect, we'll get there. Right, now to channel management. Frequency channel saturation. Right. If the demand for a specific wireless channel is too high, the channel may become oversaturated, degrading the quality of the communication. Channel saturation can be mitigated using the following channels: DASSS, FHSS, or FDM. All right, let's start by defining what saturation is. If you understand what saturation is, it's much easier to explain the techniques that are used to mitigate channel saturation. Right, so when we are transmitting or receiving using wireless devices, every wireless device, it is tuned to a specific frequency which it uses to communicate. frequency. So every device is tuned to a specific frequency. Mafrequency iwayo ndo kwabva the 2.4 gigahertz band and the 5 gigahertz band. Every device is tuned to a specific frequency. So frequencies are allocated according to ranges. Those ranges are split into channels. So we will see we are going to split this into a range. You know, the 2.4 gigahertz band is probably from 2.4 to 2.4, probably 2.5. Let's say 2.4 to 2.5 gigahertz. That's the range. Then that range is split into autonomous channels. If a specific channel is connected to a number of devices, a lot of devices, then that channel becomes saturated. How do we alleviate that saturation? Open over these three techniques. Channel selection. Okay, we'll get there. Open over those three techniques. So a bit of background. Every device in a frequency, I know Shandis. If that frequency is overused, a lot of devices uses that frequency, then we have what we call saturation. Mitigation techniques, we have direct sequence spread spectrum, a technique designed to spread a signal over a large frequency. So signal is on a device, it is spread over a frequency band. What it means is it becomes very difficult now, very difficult for other devices to occupy that same frequency. Because instead of using a frequency, let me put it this way, instead of using a frequency range like I saw, it is spread like this. So here we have my frequencies. Instead of using a very, what's the English word? I don't want to say thin. I don't want to say thin. This one, if we call it spread, let's call this one not spread. Okay, that range is not spread. But with the DSSS, we have a spread. We spread the range or frequency. We use a larger frequency band. Therefore, every other devices which wants to use the same channel, it will be very difficult for you to use because we have a set of frequencies, Panama frequencies which are being used. So that's the first technique, spreading the spectrum, having a larger frequency band. Frequency hopping spread spectrum. Guys who are doing telecommunications, excuse me, will probably get this better. Guys who are doing networking, if you don't get it, forget about it. Frequency hopping spread spectrum transmit radio signals by rapidly switching a carrier signal among many frequencies. To avoid saturation, to avoid having one frequency being used, there is change. Frequency hopping. So a device changes its frequency panenge transmit. It changes its frequencies. Device receiver is whole, sequence. How is the transmitting device changing its frequencies? Therefore, they can communicate like that. So instead of occupying that only one frequency, it changes, it hops, uses different frequencies, which is synchronized with the receiving device, therefore avoiding saturation. The last one, OFDM, the latest, which is being used, excuse me, which is being used for, I think for 4G, communication about 4G, we have OFDM. Wi-Fi edu communication, AGN, AC, they use OFDM as well. Orthogonal frequency division multiplexing. A subset of FDM in which a single channel uses multiple subchannels on adjacent frequencies. The keyword here is orthogonal. So with OFDM, we have subchannels that are orthogonal to one another, allowing them to overlap without interference. Orthogonality. Here we need to define what we call orthogonality. My channels are not orthogonal to each other. when I learned about orthogonality, my channels, they are at 90 degrees to each other. Therefore, they do not interfere. Let it end there. So keywords, key information I can highlight here. Channel saturation. Every device communicating wirelessly, it uses a frequency to communicate. Now, there are a range of frequencies that can be used by devices. If a specific channel is overused, a channel is just a smaller range. Ndatanga nekuti we have range from 2.4 to 2.5 gigahertz. That's the range of frequencies that no shandis. My frequencies, well, you will see they are broken down into my channels. So we have much smaller ranges. Probably, let me do this. Now, so on my next slide. Let's explain here channel selection. Right. I was trying to explain the 2.4 gigahertz. So this is 2.4 gigahertz here. Why it is 2.4 gigahertz? We are using the central frequency between 2.2 and 2.5. So probably pakati apa pane 2.4 apa ndosaka ichinzi 2.4 gigahertz. It's a range of frequencies. Range of frequencies from 2.2 to 2.5. Right? That range of frequencies, it is divided into smaller ranges called channels. My smaller ranges wayo anenge ane 22 megahertz. A frequency again. So we have 22 megahertz between this one, the orange one, between this and this. This is 22 megahertz. Just to know the channel. Now, if a lot of devices are using channel number 1 in the orange hue, just to know the saturation. So to avoid saturation, therefore, we have those 3 ways that we've discussed, which help in mitigating channel saturation. Getting to channel selection, the 2.4 gigahertz band is subdivided into multiple channels, each allocated 22 megahertz, separated by 5 megahertz. A best practice for 802 BGN LANs requiring multiple APs is to use non-overlapping channels such as 1619. That's another way of avoiding interference. So let's say we have chat, just a minute. Right, let's say we have multiple APs in our network. Where can I write? So we have AP1 and its coverage area. We have another AP2 and its coverage area. We have another one, let's say AP3. No, I want them to interconnect. Let's have AP3 right here. Right. If my access points are R3 use the same channel, we have what we call interference. Interference will probably lead to channel saturation. Then you can no longer communicate. I can see 1 minute left there. Maybe let's stop at channel selection. If I have the energy, we can continue to another third session to continue from channel selection. Let's end it here. Join in again. 1 hour 45 minutes. Hi.